Now I would like to talk a bit more about the joints. There are two basic types of stresses which may be present in a concrete pavement. The stresses induced by externally applied loads resulting from traffic using the pavement, and the stresses within the pavement resulting from contraction and expansion movements and differential moisture and temperature changes within the depths of the pavement. We know the rigid pavement thickness design is dominated by stress caused by externally applied traffic loading, wherefore the location and design of joints are dominated by the need to control stresses and strains induced by environmental changes within the pavement. The objectives of joint design are to develop a joining system which will control transverse and longitudinal cracking and provide adequate load transfer across joints. So the pavement will have adequate reading qualities over its service life. Joints normally should be selected to minimize the intrusion of water and incompressible solids. This figure illustrates various joint types. The common joints are longitudinal joints and transverse joints. The purpose of longitudinal joints is to control longitudinal cracking by enabling hinge release of occurring stresses. The joints are tight wherever possible to keep them firmly closed. The transverse joints include the contraction joints, construction joints, and expansion joints. The contraction joints or control joint is mainly used to control cracking. These joints do not go all the way through the thickness of the slab, but rather about a quarter of the depth or length. They serve only as a weak place in the concrete where cracks can occur and then later be sealed up. Normally, these joints do not require any load transfer device, as it can be achieved by the interlocking of aggregates. Some projects also use dowel bars to fully bond in concrete. When there are multiple concrete pavements, a construction joint is typically used. Transverse construction joints are required for planned interruptions, such as at the end of each day's operations, at block out for bridges and intersections, or for unexpected delays when the suspension of operations is likely to create a joint. Construction joints are usually spaced to line up with contraction or control joint, so they are usually not a visible component after construction. Concrete is far more capable of resisting compressive stresses than tensile stresses. An expansion joint allows the concrete or steel to expand or contract within the change in daily temperature. At the discontinuities in the pavement, some allowance has to be made for potentially high compressive forces by providing expansion or acceleration joints. So expansion joint is mainly dot, and acceleration is mainly dot. A joint layout should be designed which is compatible with the road geometry, the length of a slab, the type of joint, and the construction method. Advice on joint design and layout can be found in Road Traffic Authority (RTA) standard concrete pavement drawings, as shown in the bottom. A summary of rigid pavement design. We have learned the main types of rigid pavements: the PCP, JRCP, CRCP, and SFCP. The methods to determine the minimum thickness of rigid pavement subbase, the calculation of equivalent subgrade strength CBRE from layered CBR, the rigid pavement design including calculation of expected repetitions, allowable repetitions in fatigue NF and erosion NE, the calculation of fatigue damage and erosion damage, the total percentage of fatigue and erosion damages from different actual loading and actual group types. Accordingly, conclusions could be drawn on whether the trial design is acceptable. If not, we need to increase the base thickness until both total percentages of fatigue and erosion are less than 100%. Finally, we have discussed the joint types and functions. That's all for this lecture. I appreciate your attention and look forward to seeing you in the next lecture. Thank you.